Welcome everybody. We're going to start with integration today. In particular, these things called indefinite or unbounded integrals. And basically, what these things do is they give what's known as the general antiderivative of a function. An antiderivative being the opposite of a derivative, okay? So for example, what do we know? We know like if we were to take the derivative with respect to x of say 2x cubed, what would that equal? Well, we know that that would be 6x squared, okay? So now I'm going to introduce the notation of the integral symbol. It basically looks almost like a big S, okay? Kind of a skinny, tall S. That's the integral symbol, okay? Within the integral, we have what it is we're gonna integrate, okay? So for example, look, think about it like this. If I take the derivative of 2x to the third and get to 6x squared, then when I integrate 6x squared, it should take us back to the function we came from, 2x cubed, okay? And so the notation will look like this, okay? You'll have the integral symbol, then you'll have the function being integrated, and then you'll see this little dx notation, okay? So this and this are the integral symbol, integrand as it's known as. And the dx tells us that we're integrating with respect to this variable, okay? Okay? And so the idea is, look, again, if I take the derivative of 2x to the third and get to 6x squared, then what should be the case then is if I integrate 6x squared with respect to x, that should take us back to the 2x to the third power, okay? And this is kind of what we're going to talk about today, is this type of integration. And this is called an unbounded integral, okay? It gives us the general antiderivative. Now, before I go too much further, I'd like to kind of go through another couple quick examples here. What if I said take the derivative of 2x cubed plus 10? What would that be? Well, that's going to be 6x squared, and then the derivative of the 10 goes away. Or what if I said take the derivative with respect to x of 2x cubed minus 7? Well, again, what are we going to get for the derivative here? Once again, just 6x squared, okay? So one thing to note is that, you know, we took the derivative really of three different things, three different quantities, and we got back the same end result here, 6x squared, okay? So one thing we gotta, you know, what's the difference between the things that I've highlighted in pink? It's really just this constant at the end. Up at the first example, there was no constant. I had a plus 10 or a minus 7 in the second and third examples, right? And when we take the derivative of those constants, they go away. Well, this is one thing we need to account for when we integrate. So in reality, when I integrate 6x squared with respect to x, I am going to get back 2x to the third power, but we often will write plus c, where c is known as the arbitrary constant of integration. Okay, and all that represents is the fact that there could have been some constant hanging out there such that when I took the derivative, I got back 6x squared. Okay, so we got to get used to writing that plus c when we integrate. Okay, and let's try to figure out, you know, what's going on. How is it that we are integrating here? We'll talk about the power rule today, which is very similar to the power rule for derivatives, but in reverse. And we'll also talk about some trig integrals as well. Okay. So a couple examples here to kind of lead into the power rule for integration. Suppose I say, all right, look, take the derivative of 4x squared. I think we all know what that would be. That ends up being 8x, okay? So if I want to integrate 8x with respect to x, I would expect to get this 4x squared back, okay? Well, think about what we do when we take a derivative. We bring the power down and multiply. That's what gave us the 8. And we end up subtracting 1 from the power, okay? Well, we're going to do the opposite here. What's the opposite of subtracting 1 from the power? Adding 1. So here's how I integrate. I basically focus on x to what power? That's x to the first. So that's going to give me an x squared. Now, what would I need in front here so that when I take the derivative I get an 8? Well, a lot of you probably tell it's 4. Think about it like this, though. Here's the original coefficient that was there. I'm going to keep that. What would I now need to divide this by to get back to 4x squared? I'd need to divide by 2. Okay? And here we get 4x squared plus c. We don't want to forget that plus c. All right, let's do a couple of these, see if you see what's going on. So if I take the derivative of, say, x to the third power, we know that that's going to be 3x squared. So if I integrate 3x squared, I know I should get back x cubed plus c. Well, here's again how I do it. The original power of x is 2, so that's going to give me x to the third. I'm going to keep whatever coefficient I had to begin with. That doesn't go anywhere. But now I got to think about what would I need to divide this by to get back to 1x to the third. I need to turn around and divide by 3. And now I can simplify this. Let's see. Okay. And one more of these. Say I take the derivative of, I don't know, x to the nth power. Bring down the power, subtract 1 from the power. This means that if I integrate n times x to the n minus first, it should take me back to the x to the n power. So let's see, if I have n times x to the n minus first power. Now, look, x is the variable, n is just a coefficient. One of the properties of integrals is that we can keep the coefficient inside or we can move it outside. I can put the n in the front there. That's not going to make a difference. For example, the integral of 2x versus twice the integral of x dx, those are going to be the same exact thing. X squared plus c, this would be twice, keeping that 2, x squared over 2 plus c, and I still get back x squared plus c. Okay, so one little property is that if we have coefficients, we can move them out front. But now again, think about it. Here's the power of x. What are we going to want to do to that? I'm going to want to add 1. That takes me back to x to the n power. I have this coefficient of n to begin with. What do I need to turn around and divide by to get that n out of there? Another n. Okay? And here we get back x to the n plus c. So I'm hopeful that you're starting to see the connection between what we do when we integrate with the power and the thing we end up dividing by. Okay? Let me highlight it a little better for you here. Notice up here, when we integrated, we got x to the second power, we ended up dividing by 2. When we had x to the third power, we ended up dividing by 3. When we had x to the nth power, we ended up dividing by n. Okay? This is how we do the power rule for integration. And I'm just going to make it just more general. Power rule for integration. Okay. To integrate x to the nth power, we add 1 to the power of x and divide by whatever that new power is and add our constant of integration. Okay, so this is the big rule for the day. Okay, and this is what we're going to practice a bit. Now, before I get into too many more examples, I want to explain, there are two types of integrals we're going to see in this course. There are unbounded and there are bounded. And I just kind of want to, bounded integrals are going to be a lesson on another day. They have a kind of a more specific meaning than just finding the general antiderivative. But here's the difference, okay? Let me just kind of illustrate. Two types of integrals. Okay. First of which we'll call unbounded, excuse me, or indefinite. And they will show up in the form of the integral of some function dx. There will not be any numbers on the top and bottom of the integral symbol. That's why it's called unbounded, okay? And this gives the general antiderivative of little function f of x. In other words, suppose we have some function, we have a function I'm going to call capital F of x. Suppose that if we take the derivative of capital F of x, we call that little f of x. Then, if we integrate little f of x, that's going to take us back to the function we started with. So the integral of little f of x dx is the antiderivative, we just call it capital F of x, plus the antiderivative, okay? So up in our examples here, if this is my little f of x, my capital F of x, the antiderivative of that is that x cubed plus c function, okay? So that's just a convention. The capital F typically represents the antiderivative of lowercase f. And again, You know, it just is giving us the general antiderivative, okay? The other type of integral we see are what are called bounded or definite integrals. Okay? Here you're going to see numbers at the top and bottom of the integrand. Okay? This, think about it like this. When we take a derivative, we get a general derivative. I take the derivative of x squared, I get 2x. When I take the derivative of x squared and I plug a number in, now I'm more specifically getting the slope of the line tangent to f at that x value. Okay? So here, when we start plugging numbers into integrals, this actually gives the area between the graph of f and the x-axis on the interval AB. And again, this is a lesson for another day, but just to give you a kind of a geometric sense, I have some function I'm calling f on the interval AB. Well, this block of area can be found by computing the integral from a to b. It gives us that exact amount of area. Okay, and we'll, like I said, we'll be getting into that stuff soon. But that's the difference. So you're either going to see numbers on top and bottom of the integral symbol, or you won't. Okay, and today more about the ones you won't. Okay, so let's take a look and go through some problems and get a sense of how this stuff works. Okay, so let's start. We'll do the integral of x squared dx. Okay. So what are we going to do? We're going to add 1 to the power and divide by the new power and write a plus c. You can leave it like that. You can write it as 1/3 x cubed plus c. The choice is yours. You know, and the nice thing about these is very easy to check your work. If you take the derivative of your answer, you should get back whatever the function inside the original integral was. If I take the derivative of this, the 3's cancel. I indeed get back x squared. Okay, so that checks out. Okay, another example. Let's look at something like 3x to the 5th. Okay, so again, I keep the coefficient that's there. I'm going to add 1 to the power of x, and I'm going to divide by the new power, and I'm not going to forget the plus c. And if I simplify, we're looking at 1/2 x to the 6th plus c. And sure enough, if I take the derivative of that, I do get 3x to the 5th back. Okay. And something like this, maybe it doesn't always simplify as nicely as we'd like. Again, I'll keep the coefficient of 3, add 1 to the new power, and divide by the new power. Okay, so we're getting 3/8 x to the 8th plus c back here. All right, so that's the idea. Again, watch for the powers. You need things written to powers to do the integration, just like with the derivative. So if you see something like this, you want to be careful, okay? This is not going to be... This is not 1 over, okay, x to the 4th over 4. It doesn't work like that because you got to think about what power of x we really have here, okay? So we want to make sure to rewrite this as x to the -3rd power. Now we can go ahead and apply the power rule. So adding 1 and dividing by the new power. We get that, which I could write as -1 over 2x squared plus c. Okay? So again, let's practice a few of these. Okay, give that a try. If you need to pause and then hit play to see. Adding and dividing and rewriting. Okay, we can integrate a constant function. What if I ask, what's the integral of 5 with respect to x? Basically, we're asking, what is 5 the derivative of? Okay, well, you can use the power rule on this if you want. Think about that. That's 5 times x to the 0 power. That's still the number 5. And now I could add 1 to my power, divide by the new power, and we simply get back 5x plus c. And think about that. If we look at the graph of y equals 5x, that's a line with a slope of 5. And yeah, the derivative is just 5. Okay, so 5 is the slope of the 5x function. Okay, so you can integrate constants. You're basically just tacking on an x. So for example, what if you just saw the integral of dx? Well, how many dx's are in there? That's 1 dx. So this would just be 1x plus c. All right, All right, the integral of the square root of x. Okay, what is the square root of x the derivative of? Well, again, since we have a radical, we're going to rewrite that as the 1/2 power, and now we can integrate. Adding 1, we get the 3/2 power divided by the new power, and then cleaning that up to divide by 3/2 is to multiply by 2/3. And there you have it. Okay, leave it like that. You can write it like that if you choose. Okay, whatever. But there you go. All right, next up, suppose we have an integral where we have something like this, x squared times x cubed minus 2x. So the thing to look out for is the fact that we have a product. And if we were to take the derivative, we'd have to use the product rule or find some other way around it. So, you know, there's going to be rules for integration for dealing with products and such, but we haven't learned them yet. So much like when we began our derivatives unit, today with integration, if we see any sort of like product, quotient, or chain, we're going to have to find a way around it, okay? So the point of the next couple of examples is kind of knowing what to do if we run into these situations. So this one's actually not too bad. We want to avoid the product, so we're going to distribute here, okay? Before we begin, that's what we'll do. We'll distribute. Now we can go ahead and integrate. So x to the 5th, I'm going to go x to the 6th divided by 6 minus, I'm going to keep the 2. X cubed will become x to the 4th over 4. And again, if we want to clean it up a little bit, 1/6 x to the 6th minus 1/2 x to the 4th plus c. Okay, so if there's a product, distribute that through to begin. If we see something like this, x to the 5th plus 2 divided by x cubed, this is a quotient. We would need the quotient rule to take the derivative, so it means we're not ready to integrate. We're going to get around the quotient. How are we going to do that? We're going to use a common denominator of x to the 3rd power to break this up. Now we can simplify. The first term becomes x squared. The second term is 2x to the negative 3rd. Now we can use the power rule. We got to round the quotient. Okay? Integrating x squared, adding 1 gives us a new power 3 divided by 3. Keeping that coefficient, integrating x to the negative 3rd, new power of negative 2 divided by negative 2 plus c. 1/3 x cubed looks like minus 1 over x squared plus c at the end of the day. Okay? All right, next example. Suppose we see something like this, and we have a quantity raised to a power. You should be thinking chain rule. But again, we don't have a chain rule for integration today, so we got to get around it. And to get around it, we're going to square that out. And in doing so, we're looking at x to the 8th. 3x4s and 3x4s is 6x to the 4th, and then a plus 9 at the end. And again, now we can go through term by term and integrate this thing. X to the 8th will become x to the 9th over 9. 6x to the 4th becomes 6x to the 5th over 5. 9 becomes 9x plus c. Okay? So again, little things we can do to get around product, quotient, and chain rules. Okay, just a couple examples here. What if I have something like 4 over the cubed root of x squared dx? Okay, so think about how you're going to rewrite that. I'll keep the 4, and then that's going to become x to the negative 2/3 power. Okay, and now integrating, I'll keep the 4. Now be careful, negative 2/3 plus 1 is positive 1/3. Divide by the new power. Plus c, 4 divided by 1/3 is 4 times 3, that's 12. X to the 1/3, 12 times the cube root of x plus c. Okay, so again, rewrite things with powers. A couple more of these, and then we'll look at some basic trig ones. Okay, think about this, x to the pi power. The integral of x to the pi power. All right, well, that's the power rule. What are we going to do to the power? We're going to add 1 and divide by the new power. And that's what the antiderivative of x to the pi power would look like, just like that. Notice another thing. After we integrate, the integral symbol and the dx symbol go away. Okay, those are like operational symbols telling us to integrate this thing with respect to that variable. Notice after you integrate, you don't see an integral symbol anymore, you don't see a dx anymore. So try to work on that proper notation. Similar example last, what if I have, say, x to the e power? Same exact idea. If it's x to a power, we add 1 to that power and divide by the new power. And so if I had like x to the radical 3, what do you suppose that's going to look like? X to the radical 3 plus 1 divided by radical 3 plus 1. And your constant. Okay. Other things to look out for are the variable. If I said, look, what's the integral of 7 dy? It's not going to be 7x plus c this time. What do you suppose it's going to be? 7y plus c. Okay? Or suppose I have something like the integral of w dw. So w is the variable. That's w to the first. So we're going to get w squared over 2 plus c. Or if I have something like the integral of dt. That's 1 dt. So when I integrate, I get back 1t plus c. Most of what we're going to see are going to be dx's to begin, but throughout the course, we'll see lots of different variables that we'll be integrating with respect to. Okay, so you just want to look out for that. All right. Sometimes we do what are known as initial condition problems. And basically what we're going to do is we're going to find the antiderivative. I'll word it like this. Find the equation for y given dy dx and 1 point on the graph of y. All right. So for example, let's suppose we're told dy dx equals 3x squared plus 2x, and on y we have the point, let's say we have the point 1 comma 3. Okay, so here's the idea. We have dy dx, that's the derivative. We want y, that's the original function. Okay, so it's like if we're given f prime and we want f, we're going to integrate. So to get to y, we're going to integrate 3x squared plus 2x with respect to x, okay? So integrating that, we're going to get 3x to the third over 3 plus 2x squared over 2 plus c. In other words, x cubed plus x squared plus c here, okay? That's our general antiderivative. This is what y equals, okay? Y equals this integral. But now that we know a specific point that the graph goes through, we can actually solve for c. When x is 1, the y value is 3. So using our initial condition, subbing in for x and y, we can now solve for c. And we get that value, and so the official y function here going through that specific point becomes x cubed plus x squared plus 1, okay? So again, knowing a point that the original graph goes through allows us to solve for that arbitrary constant, okay? And another example similar, suppose f double prime of x is x, f prime of 0 equals 4, and f of 0 equals 7. Find the f function, okay? So here we're starting off f double prime of x. So what are we going to do? We're going to go from f double prime to f prime back to f. So f prime of x will be the integral of f double prime of x, which is going to be the integral of x. And if we integrate x, what do we get? X squared over 2 plus c. Now before we go any further, we're going to want to figure out what the value of c is using this initial condition, okay? So I know that f prime of x is going to be 1/2 x squared plus c, and I know that when I plug 0 in for x, the whole thing equals 4. And so it looks like c itself is going to be 4 here. So f prime is 1/2 x squared plus 4. Okay, Now we can work our way back to f. So f is going to be the integral of f prime of x. So that's the integral of 1/2 x squared plus 4. Keep the 1/2. I'm going to get x cubed over 3 plus 4x plus c. Okay, 1/2 divided by 3 is 1/6. Let's make it look a little nicer to write it like that. And there's our f function. Again, using this initial condition. The whole thing equals 7 when x is 0. And again, it looks like c is going to be 7 here. And our official final function, 1/6 x to the third plus 4x plus 7. All right? And now the last thing I want to do is just touch on some basic trig integrals. And basically all I'm going to do here is show you, remind you more or less, the antiderivatives of your 6 basic trig functions. Okay? The derivative of cosine is negative sine. So the integral of the sine function will actually be negative cosine of x plus c. And you're going to have to put a little bit of thought into the signs here, positive and negative. It's going to be kind of backwards to what the derivatives were because we're going backwards. Suppose I want to integrate the cosine function. What is cosine the derivative of? Sine of x. Secant squared x is a basic integral. Why? Because secant squared x is the derivative of tangent x. Okay, next up is the integral of cosecant squared x. Well, negative cosecant squared x was the derivative of the cotangent function. So if we integrate this, we get back to the negative cotangent function. Integral of secant x tangent x takes us back to the secant function because the derivative of secant x is secant x tan x. And last but not least, cosecant x cotan x would be the derivative of the negative cosecant function. So you want to know these and just study them up a little bit, okay? And then you can see some examples like the following. Suppose we saw, okay, what's 1/2 the integral of sine x dx? Again, we keep coefficients that are out front, and the antiderivative of sine was negative cosine of x. And that's that. You might see the integral of 3 secant x tan x. Well, keep the coefficient, and that's just number 5 here. That's going to be the derivative of 3 secant x. And last but not least, the integral of 1 over cosine squared x. Actually, let's change the variable. Let's just to make it something different. Cosine theta d theta. Can you figure that out using these rules up here? Well, if you're on the right track, you realized I got to rewrite this as secant squared theta. 1 over cosine is secant. And the antiderivative of secant squared x is tan x. So the antiderivative of secant squared theta, tangent theta, plus c. All right, folks, there's your basic antiderivative rules for trig functions and the power rule. We got a long way to go, but we'll get there. Have a good day.